A business in its rawest form is a collision of parts. Materials arrive, data streams update, and human labor tries forcing it all together. Without structure, it's a chaotic swirl of energy burning through capital. To generate value, you must force that chaos through a transformation process. You take those raw inputs, apply work to them, and turn them into outputs that customers actually want to buy. Process design provides the exact blueprint for that transformation. It specifies the sequence of activities, the allocation of resources, and the equipment required to move from the input funnel to the final product. Every choice made in these decision bubbles defines the boundaries of your operations. The sequence of activities dictates your quality, your production speed, the dependability of your deliveries, your flexibility to change, and your total cost. This design serves as the physical manifestation of an organization's business strategy. Consider two companies. One pursues a market through extreme cost leadership, while the other offers highly customized premium solutions. If the cost leader uses a highly flexible but slow manufacturing layout, their labor costs will spike. Their business strategy fails before the first product reaches a customer, simply because their operational blueprint doesn't match their financial goals. Process architects face an inescapable constraint: the trade-off between output volume and product variety. Charted on two axes, this dictates that to produce more units, your process becomes increasingly standardized. To achieve efficiency, you sacrifice custom variety. Every operational facility, from a bespoke tailor to a massive oil refinery, sits somewhere on this exact curve. Mapping specific operational types along this curve begins in the extreme top left with the project process. This is the domain of highly customized one-off outputs. A bridge construction site illustrates the unique physical constraint. The product stays completely stationary. You must bring the resources, cranes, and labor to it. Moving slightly down the curve to increase volume introduces the job shop process. A custom metal fabrication shop operates here, producing a wide range of specialized parts in low quantities using highly skilled labor and adaptable machinery. The operational flow is intermittent. A product moves in a non-linear fashion between different functional areas, drilling, then cutting, then back to welding, creating complex and varied routing paths. While these top-left processes offer maximum flexibility and bespoke quality, they result in the highest cost per unit and the longest lead times. The middle of the matrix contains the batch process. Here, you balance flexibility and efficiency by grouping identical items together. A local brewery makes one type of beer, finishes the run, and then switches the line to another. The vulnerability of batching lies in the setup time. Every product switch requires machinery to stop for cleaning and recalibration, downtime producing zero value. To eliminate that downtime and drive up volume, you transition to a line process. On an automotive assembly line, standardization takes control. High volumes of identical units move along a fixed sequential flow, reducing the need for specialized skills. Pushing to the extreme bottom right gets us to the continuous process. This is the realm of oil refineries and chemical plants, where production runs 24/7 with massive capital investment and virtually zero human intervention. Absolute maximum scale requires the removal of human variability, stripping away flexibility in favor of rigid, dedicated infrastructure. Zooming in from the high-level matrix allows us to analyze the internal mechanics of a single operational sequence. The critical metric here is the throughput rate, the speed at which completed units successfully exit the final step. If one node operates slower than the surrounding steps, it creates a bottleneck. The flow breaks down, and materials pile up directly in front of the slower station. That backlog represents tied-up capital. This work in progress inflates lead times and obscures systemic waste that would otherwise be visible on the factory floor. This reveals the golden rule of capacity. The total speed of your entire multi-million-dollar system is dictated by its single slowest bottleneck. For decades, that diagonal volume-variety trade-off was an absolute law of manufacturing. You had to pick a side. Today, Industry 4.0 technologies, connected IoT sensors, AI scheduling, and collaborative robots challenge those inherent physical limits. By using programmable automation and virtual digital twins, modern assembly lines can switch between product variations instantly. This eliminates the massive setup delays that plagued batch systems. These tools are physically bending the curve. By expanding the boundary toward the top right, we enter a new operational zone known as mass customization. Advanced technology allows an operation to achieve high-volume efficiency without sacrificing bespoke variety. Even the most advanced process will decay if left alone. Equipment wears down, and variations creep into the supply chain, causing efficiency to drop. Organizations fight this through Kaizen, or continuous improvement. This involves the daily elimination of waste, one minor tweak at a time. The alternative is business process reengineering, or BPR. This is a radical, ground-up overhaul of a core system. Continuous improvement is culturally safe. Everyone participates, and a bad idea is easily reversed. Reengineering is high risk. You are tearing out the foundation of your operations, and if the new system fails, the entire workflow halts. World-class operations require both the daily discipline of continuous improvement and the courage to occasionally execute a radical reengineering leap. These models work perfectly on paper, but operations managers must implement them in unpredictable environments, such as the dynamic landscape of Southern Africa. External systemic variability is a constant threat. Inconsistent electricity grids, port delays, and infrastructural inefficiencies frequently disrupt even the leanest process flow. Adaptation requires buffering. While lean theory seeks to eliminate all excess inventory, real-world operators strategically use extra stock or time to absorb these external shocks. This forces a shift toward operational robustness. You aren't just designing your physical footprint for perfect conditions, you are designing it to survive severe unpredictability. The ultimate test of process design is not how fast it runs in a theoretical simulation, but how resilient it proves to be when the real world pushes back.